I sent you guys an announcement yesterday of just reminding about the problem set being due on Tuesday and saying that I posted the next one here. Not problem set, sorry, programming assignment. Problem sets keep on coming every week, or homework. So programming assignment, the next one you can almost start with today. We'll just finish up the splines and then you just keep on going. And you realize that now they're going to keep on coming every second week. So you've been kind of free from, you better get used to this programming assignment. Big important part of the course. I do agree that it's difficult to ask long programming questions on the exams, which is the reason the programming assignments are 20% of your grade at the end. And it's just, I believe it's an important part of teaching this. So take them seriously, please, and let me know if you have any questions on it. Too loud now. Let's see. Where are we? We are, I'm going to try to finish up splines and then go into chapter 4, which I didn't have time with last time. 4 is, again, a new topic, differentiation and integration. Let's go through the splines again. So this is a kind of a cool topic. On the slides, going back to chapter 3, well, just a few words about what we did about the Hermits. So 3.4 first. We did generalize the idea of interpolating through points, or Taylor interpolating points and derivatives, and said, how about whatever you want? You have a bunch of points, and at each point you decide if you want the function to go through it, or go through it with a given derivative, or second, whatever. And you can have any combination of this, and that's the generalized into these oscillating polynomials. But the 3 important special cases are here, and it's kind of nice to see how they pop out. You could do anything, but these are what we mostly do. And if you just have one point and lots of derivatives, it's a Taylor. If you have a lot of points and only values, then that's what we used to do, Lagrange, right? But how about something in between? So a particular important case is the Hermit polynomial, where you insist on, you give me a bunch of points, you also tell me what derivatives you want at those points, and I find a polynomial through them. Okay? The degree of that polynomial is kind of trivial. You just count coefficients and conditions, like always. So if you have 5 points and you want values and derivative, that's 10 conditions. You better need a 9th degree polynomial, which might be crazy. Anyway, we have this nice theorem telling you exactly what those polynomials are. And it's a little messy, I think. The h's and the h hat are a little messy. You can just plug in. It's actually very easy to prove this is the case. But what I would like to really see is why the top expression works out. How come we can define functions h and functions h hat such that you can just multiply them by f and f prime and get this polynomial? And it's exactly the same idea as Lagrange, namely that these polynomials h and h hat have very specific properties. They are 0 almost everywhere, and they are 1 at the point, the h's, but they also have 0 derivative everywhere. And the h's hats do the same thing, but with the derivatives. So by adding them up, you can trivially get these out. So again, like with Lagrange, it might not be the form you actually want at the end. You might like ax plus b, a plus bx plus cx squared. This might not be what you want. But these h's and h's hat have very nice properties, which means that you can just write the interpolating polynomial like that. We, of course, have an error term as well, as expected, and not too different from before. So these are these Hermit polynomials. I also mentioned that really the nice way to do this by hand are these divided differences. I like the divided differences already before, in the sense that we could do like a 5th, or whatever I did, like a 5th degree polynomial with simple hand calculation. It's even more powerful for the Hermit. And it's a little trick you have to learn, and it's really explained by the first 2 rows here. Namely, duplicate your x values, and you can call them z just because of that. And there will be that, because of duplication, you will dividing by 0 a few times, and that's where you put in derivative. And in the book, you can see a short explanation for this. It's actually very easy to see that these divided differences really correspond to derivatives in the limit. So if you want to understand this, where it comes from, imagine you're not quite duplicating them, but you're making a little step. So in principle, instead of having, so this is the setting. You're telling me values and derivatives, right? And you want to find a polynomial that does that. Okay? So that's what we're doing. Just in terms of these differences, you can imagine that approximately, now I'm going a little bit into the next topic of today, namely numerical differentiation. You can imagine that instead of giving me derivative, suppose you didn't know how to do Hermit. You don't know that Hermit exists. You only know Lagrange. But you want this to happen. You could say the following. OK, I don't know how to do derivatives, but why don't we put that guy there? And then I do a little step with the given slope. You see that trick? Now it's back to Lagrange. I'm really just going through those points. But approximately, of course, I will get the slope that you put into when you created those two values. So what I'm saying in principle is that you have a number, f of x1 here. But you also have a derivative, and you put a point at x1 plus a small number, delta. And you move it down according to the slope. That kind of will approximately give you, without knowing anything about her mid. Okay? And now this little trick is obvious by letting that delta go to 0. If that delta goes to 0, these points will end up on top of each other, which is fine. The only issue is that when you compute this, you will get division by zeros when you compute differences, but that ends up being exactly the definition of a derivative. So I think that's the easiest way to see it. Go back to the definition of derivative, do this little finite delta trick, and let that go to 0. Of course, that's how you understand it. In practice, of course, it's much easier to use. Just following these two rules, I did a big example. I think I did 2 examples on the blackboard last time. One simple, and one fairly complicated. Even though I tried to use zeros and ones for everything, still, I think I did 3 points and derivative on each. That's 6 conditions. That's a 5th-degree polynomial. And it just came out very easily by just writing down these rules. So very practical, I think. All right, moving on to these splines. I did a demo saying that if you have a lot of points, you really do not want a high-degree polynomial through them. I showed an example with just 10 points or 11, and the polynomial did this. That's what polynomials do. We don't like polynomials of too high degrees in general. So how do you do, and this goes back to your, or this really couples to your problem set. I'm going to talk more about it. Let me just show you a picture. In your new programming assignment here, I want you to draw curves of this form, which are so-called spline curves, parametrized spline curves. And how could you do that? Do you really want to put 1, 2, 3, 4, 5, 6, a 5th-degree polynomial here, or should it be lower? And what the world seems to have realized in a huge number of fields in engineering and computer graphics and science is that 3rd-degree polynomials is a nice compromise. But you want this curve to, there are more than 4 points. So how do we do that? And the answer is that you do piecewise 3rd-degree polynomial. Piecewise meaning that you divide each of these intervals into chunks, and you put a 3rd-degree polynomial in each of them. So if you look at my dashed line there through the points, this is not a function. This is a parametrized curve. And we'll come back to that. But just for now, since this is the only picture I have, basically each of those curves would be a 3rd-degree polynomial. Okay? How do you make it look smooth and nice in between? That's just conditions. That's just equations. So it's kind of nice. Let me draw. If I draw it here, it's a little bit better. Because instead of saying, so this was her mid going through all those points. If you instead just tell me that you want these points, and 3 is kind of silly because it's not enough. But the idea would be that you put a 3rd-degree polynomial here. So 4 numbers will give you whatever those numbers are. And then you put another 3rd-degree polynomial here. OK? And it seems completely overspecified, because I only told you that this 4 3rd-degree polynomial should go from there to there. That's 2 conditions and 4 unknowns, right? This guy goes from there to there, 4 new unknowns and 2 conditions. So I did mention that suppose you said that it was not a 3rd-degree polynomial, but a 1st-degree polynomial, then we would be done. And that shouldn't be a big surprise, because all I did was to draw a straight line and a straight line, right? But that is a perfectly valid interpolant of these points, right? And in another language, I would say I do a piecewise 1st-degree polynomial between each point. And it happens to be that the conditions exactly work out. 2 unknowns, 2 numbers. 2 unknowns, 2 numbers, etc., right? All right, so let's go up to cubic. Then we have only used up half of our conditions. We need a bunch of more conditions. And of course, the conditions are going to come here. And I call those conditions smoothness. I want not just the values to join, but the derivatives. And it turns out you can do second derivatives if you count the condition. And we did count the conditions last time. So that's exactly what it is. You do this, and you say that this guy and this guy must have the same derivative and the same second derivative at that point. Then you get almost everything, except the little issue that at the very leftmost point, if you have a lot of them here, you don't have a left spline to say equal derivative here. So you need to say something else here. And there are 2 ways to do that. Summarizing all these conditions, it goes into the definition of what a spline is. So a spline is what we said, or cubic spline interpolant, is defined by all these conditions. Each little segment is a cubic spline. They agree on the values. This is an easy condition. This is what you would do with a straight line. At the endpoints of each interval, it agrees on the values. C is kind of nice because of the symmetry with D and E. But if you really think about it, it really says that pairwise, these guys should agree on value. So this left one at this point should be equal to this right one at that point. But that comes from telling that it should go through the data point. So I said that B implies C. That's fairly straightforward. But then come these other things. Derivatives equal. Second derivative is equal. What does that give you? You know I like to have n, what do? I like to have n plus 1 points, right? Yes. I have x0 to xn, so I have n plus 1 points. That means that these conditions here are only going to happen at n minus 1 points, because you cannot do the left and you cannot do the right. So conditions D and E only show up n minus 1 times. Okay? And we're lacking 2 conditions, and they are the endpoints. And we're going to use both of these. But basically, you need to do something at the endpoints. And it comes from physical considerations or anything. It's just not fully specified. So that's the issue with these. You can just turn the crank and do all this. I did an example that was fairly easy. 0, 1, 1. I like my simple numbers here, right? You have one polynomial. We call it S0, which is really just a plus bx plus cx squared plus dx cubed. But I better call it a something, right? Because there's going to be another one coming up. So let's call it a0. And then you have a1. And the only thing that maybe you wouldn't have done the same is that I do subtract the left endpoint of the interval from these polynomials. And in a way, the way I'm going to end up solving this, I wouldn't have to do that. It doesn't really matter, because you could write it in any form. But this turns out that the a's are very easily given. But you should all see that this is for sure a polynomial. I just moved it around a little bit. Now what? Well, then we did it, and I'm not going to repeat that. But we wrote out all of these conditions. In particular, I said that S0 at 0 equals 0. S0 at 1 equals 1. That's condition B, half of it. S1 at 1 equals 1. S1 at 2 equals 1. Note, I never evaluate S0 out here. I never evaluate S1 out here. They only live in their interval. Quite straightforward. Then I go to condition D, and I say I only have one internal point. There's only one condition, and that's this guy here, where you say that S0 prime, the derivative of S0 at 1 equals S1 prime at 1. Same with 2 derivatives. And now I need my boundaries, which I think I used the free one, which says that the second derivative of S0 here is 0. The second derivative of S1 at point 2 is equal to 0. Just write them all out, and we got a bunch of equations. Anyway, here's what happened. We had one equation, let's say the easy one. S0 at 0 is clearly equal to A0. And I wanted that to be equal to this value, namely 0. That's an equation that can be written as 1 times A0 equals 0. Okay? Next equation was S0 at 1. That's A0 plus B0 plus C0 plus D0, right? Equals that number, which is 1. As an equation, that's 1, 1, 1, 1 times A0, B0, C0, D0 times 1. My point is this is just a linear system of equations. You have 8 coefficients or unknowns. You have 8, I used to call them conditions, but they are, of course, equations, right? And it's all linear because these coefficients are never doing anything but multiplying things linearly. Straightforward. These equations, of course, get a little messy now because now I start differentiating. But you know, it's pretty straightforward. So this shouldn't be big magic, and you can solve it. I did tell you that I'm being stupid solving it in this form, but I'm doing it almost on purpose. For example, the idea of writing it in this form means that the a's are immediately given. You can see 1 times a0 is equal to 0. Why did I even include a0? I should have excluded it, right? And just simply eliminated it. Similarly, what are the other ones we're given almost for free here? Yeah, the a1, of course, is also immediately given. So is that really a 0? Maybe I messed it up. No, that's good. Oh, it's equal to 1. So 1 times a1 is equal to 1 as well. So the a's you could throw away immediately. That's the nice form about this. And you can throw away more of them. But let's not be too smart. Let's just do it. So the computer way to do this would be to just solve the system, and you're done. And let's see, just to show you that it's possible. But it's a little too big to write by hand, but we can do it. 3, 4, but it's very easy to make mistakes, of course. 1, 1, 1, 1. 0, 0, 0, 0, 1. You see, that's half of it, right? And then you keep on going. But now I will mess it up, I'm sure. Especially since I don't remember exactly the spaces there. We'll see. 0. Is that really it? Yeah. And the last one, 2, 6. And I think last time I wrote a -6 incorrectly. Anyway, this should be an 8 by 8 matrix. And there's a right-hand side as well, which is 0, 1, 1, 1, like that. And you really just do u, or coefficients, right, equals a backslash b. If you know MATLAB well, you know that. And again, this is the last part of this course, but we're going to need to solve linear systems. If you want to solve ax equals b, you do a backslash b. Backslash is like inverse. F, sorry. And there are coefficients, and let's see. I think I messed it up. Because this is not what I wrote here. Oh, it's very similar, though. All right. Anyway, let me check quickly since I have the numbers here. So the first 4 equations are trivial because they came from plugging in 0 and 1 and 2 on these ones. They're pretty easy to get. The other ones, I guess, is easier to mess up, but I guess I did, let's see, 1, 2, 3 of the first one equals B1. Yeah, I would say row 5 is correct, if you guys have that. And then I had a 2 of C plus 6 minus 2. The next one is correct, too. And then I had 2 plus 6, OK. And 2, maybe it is correct. All right, anyway, I'll check because I have another way to check this. So, this is the way you do it. You get the coefficients out, and you, how would I now plot this? Is it super easy to plot this function? There's a slight issue with plotting this function. I mean, it's really just a function. But what function am I talking about? It's a piecewise function. It's a little annoying, right? Because if you want to evaluate this function, you got to tell MATLAB that if you evaluate between 0 and 1, you better use this expression. And if you evaluate between 1 and 2, you better use this. If you evaluate outside, you better say, no, I can't do that. You know, it's a piecewise function. We haven't done that so much before. I wrote a little utility for you, but just so you know, it's not just plugging in. Like almost always before we have functions, we just write them in MATLAB and we're done. It's a little more difficult. Conceptually, it's easy to see, but just in MATLAB, you have to choose where you are before you can evaluate. There's a way to do that in MATLAB. So I have a little function that I call spline eval. So let's see what we have here. We have, I've given you a bunch of functions. And by the way, as always in homework, please double check yourself, do everything with this, but also know that you can compute it by hand. For the spline example in the book, I would highly recommend that you actually do it by hand, and then you can double check with my functions. But these functions can solve all these problems. So here's a non-clamped spline. You shouldn't read this function. It's based on the book and the expressions there. But the reason I wrote this out explicitly is that I don't really care about all the algebra. They're doing a bunch of smart tricks to make the algebra easy. And it's not that easy anyway. And you don't know what a sparse matrix is in MATLAB. So just focus on the conditions and how to set it all up. And know you can do it by hand, but then you can use the function as a black box. But the way this black box works is that it really just takes points and values, and it outputs the spline coefficients. And why are there only B, C, D when I also had an A? Well, that's based on the observation that if you write it like this, all these A's will really just be your values here. You can think about that. But in my case, A0 ended up being 0, A1 ended up being 1. So the data you give are really these coefficients. So if we want to do this example, I would do the following. 3 points and 3 data, let's call them A for now. And then you can compute these coefficients by non-clamped spline of x, A. And there get some numbers out. And it shows that I probably was right before. If we look at my coef from before, you can identify here, first of all, this was A0, remember? That's 0. This was A1, that's 1. That's kind of data. That's what you gave me anyway. This is B0, and it agrees with my function. This is C0, so it was right. OK? But my function did it in a smarter way, but I think this is more educational. It really just spells out that there are 8 equations and 8 coefficients. It's no magic. It's really quite straightforward. Anyway, what you might appreciate, but of course this function was really easy to use. I didn't have to set up it's pretty quick, right? I also gave you a function that I call spline eval. You're going to like this one. It does the thing I just said. Where am I? And picks the right polynomial. So eval means evaluate. Spline evaluate. So if you want to see how simple it can be, it's really this short. You got to figure out where you are, basically. There's some logic going on. But don't worry about that if you don't like it. The way we use it is that you give the spline. So I would say a spline is given by these 5 arrays. You see why? So you have the x points. I need to know those. You have the a's, which we agreed were equal to the data, actually. So they're not that, it's not that magic. And then you have the b, c, d that you just computed. OK? So those 5 arrays give you the spline. And then I use this notation before. I do xx as a bad name of saying this is where you want to evaluate. Okay? And out comes yy, which are the interpolated points. So how do I plot this? Kind of like any other function, you need a new x. And it makes sense to go between 0 and 2, right? And then you can now plot xx, comma, spline eval. And here you put your entire function. This is the spline, right? See, that's that easy? So it's kind of nice to write utility. And there is the function. Why don't we put in the circles as well, so to make it look exactly like what I did here? That's what's x comma a, right? And I like bigger markers. So that's what we did. And you know, I don't know what to say about it. It's really a piecewise. It's not one polynomial. The whole blue curve is not a polynomial. It's a piecewise polynomial, which means that segment-wise they're polynomials. And it all works out. Just to make it a little bit more interesting, let's add a bunch of more points. So we could do, since we have the function now, we can do a lot of points, because I promised you that was going to be nice, right? And I don't know what data you want, but let's, for now, we could do a random data. So I guess I now have 11 points. And it's kind of crazy. That's a little too, well, the spline doesn't really care. It's just that it's not a lot of correlation there. We could do it. And let's do it. So I call it y now. What should I rename it? I mean, it might be instructed to actually call it y. These are the data, x and y, right? But remember, the spline was chosen so that a's are equal to this data. So maybe the best way to write this is to say a is equal to y. And the spline comes from this. So here are a bunch of coefficients that you would hate to compute yourself. In fact, if you did it in this way, the size of that matrix would be, let's see, 0 to, I have 11 points, so I have 10 polynomials times 4 coefficients. If I did it in this naive way, I would have 40 equations. Then, of course, you might identify that all the a's are trivial, so you have 30. And in fact, the trick in the book that is used in this function is to reduce it even further. But there are some more patterns. But it doesn't matter. It's just a linear system. And here's the spline. Let's plot it. Same as before. And it's probably going to look crazy. Oh, I did something wrong. Yeah, what did I do wrong? XX is wrong, right? Let's run all the way to 10. So this is the widely popular and celebrated spline. The idea that you give a lot of points, and it, in many, I mean, actually, it's not very pedagogical, because it still looks like it's crazy up and down, and it's 2. But that's because the data is bad. Remember, let's do my example from before. Remember what I did was that I did points between -5 and 5, 11 points. And I interpolated a function that was 1 over 1 plus x squared. So these points look very simple. You see the 8 points? It's a 1 over 1 plus x squared. Very nice and smooth function. Then I fit the polynomial. I probably have that history here. Yeah, there it is. And then I plot. Isn't history nice? I need a new xx and a new yy. That's OK. Let's do that. So this is repeating what I did last time. And this might be OK. So I had 11 points just like before. But now they're not random. They are really just a nice and smooth function. The green curve is that nice and smooth function, 1 over 1 plus x squared. But let's see, a 10th degree polynomial, the red curve, is a disaster. That's not a good idea. So let's now add to this spline through these points, which I, of course, have to compute. And the way I do it is to say a is equal to y. And here are these guys. And I'm telling you, the boundary conditions are an issue. It's really a big issue. In this case, it would be better to use that other condition, which says that you can tell me what it's a little bit like Hermit. You can tell it what the derivative should be at the corner, since I know it's a function. But if you're out in a real situation, maybe you don't know the derivative. But I'm just saying, you have to choose a boundary condition, and it's not clear. This is probably not the best choice. There are going to be lots of coefficients again. I don't want to see them. But now I'm going to add here at the end, xx, comma, spline eval of x, a, b, c, d, xx. That's how easy it is to use. So now hopefully we'll get a new curve. Well, let's look at this curve. So over here, it's right on top of the other one, right? So it certainly fixed the issue of doing that. By any standard, this is better. Maybe if you zoom in around here, you'll see some issues. So I think the green one was the actual function. The red was the bad polynomial. And the spline is right in between here. So they disagree a little bit, because it's pretty far. A lot of stuff is going on here at this corner. But if you go further down, you see how the spline is really doing a quite good job of tracing here. So in general, this is a better idea to interpolate functions with a lot of data. That's the end of basically the takeaway message. And again, your problem in the book are such that you can set these up and simplify. I have in the slides, I wrote what I wrote in the book. Turns out you can simplify this down to only solving for the c's. If you write it and set up the expressions right, it's kind of nice, right? I mean, you can imagine people were sitting there, they didn't want to solve the 40 by 40 system. And if they figured out you can solve a 10 by 10 instead, that was amazing. So that's what they figured out. And here's how to do it. I don't think that's the critical part. It's implemented in the functions. The expressions differ a little bit if you make it clamp, that other boundary condition. And I'm sure I gave you an exercise on both. But the way you should remember this is to know exactly the definition. And when you know that, you can in principle solve anything. And whether you want to do smart algebra or not, that's not so important, right? Then also double check with my functions. You're going to love my functions for the problem sets, for the programming assignment, because then it gets messier. So then it's nice to use simpler functions and for evaluate. Let me just say a little bit about parametrized curves. I know I would totally expect you to just know it, but I want to point it out still. How do you represent curves? So I told you that these splines are very popular in the real world, for example, computer graphics or CAD or anything, because they used to represent objects, right? And they actually generalize to surfaces. And anything you see in a Pixar movie is done with spline-like things called subdivision. But it's the same type of idea. But just let's talk about a curve to begin with. So the dash curve there. I'm an engineer. I'm designing a new whatever, right? And I want that shape. And I decided to model with splines. And I have these control points, the little dots. So that's what they actually do. But here comes the trivial part. Is that a function x? Is that a function y of x? So that's kind of elementary, at least calculus, right? Saying that's definitely not a function. And one obvious, it almost is, right? But there are points where you have two y values for one x. So it's definitely not a function. Even if I didn't have that, it would not be a good idea to make it a function. So what do I do instead? I make it a parametrized curve. So I make up another variable that typically runs increasing from beginning to end. So I make up a value that is equal to 0 here, and it increases all the way here. So as it goes, it traces out the curve. And then I have two functions of that independent variable. This is a parametrized curve. The simple example is the following. If you want to do a half circle, you could do it with a function, right? And you could say y is equal to square root of, and already here you see some issues that is turning, you get infinite derivatives and stuff. But you could also say, and by the way, this will have a direction. You could also say that you have a variable s that goes from 0. Let's start, I don't know how I want to do this. Let's make it just a regular theta, right? So it goes from 0 to pi half. And then, so this is s that goes from there to there, right? And that's my independent variable. And my x is now a function of that s. And it's equal to what? Cos, right? And y of s is sine of s. So these two formulations, and I guess this would have to tell that x is 0, 1, right? These two formulations are kind of identically describing that curve. I guess you could argue a few things. This one has direction, that one has not, although it kind of has through the x. So, but it's clear if I now let this turn around, go back here, this one is dead because it's not a function. This one works fine. So in general, this is what you want to do. When it comes to the spline, I think your biggest problem here is if you just realize this, you will keep it apart. But in all my functions, in all my demos, I have x and y. And if you look at this now, is this x now the x that I used to be an x? No. This is now the dependent variable. This is going to be the y. And here's another y, right? Fairly straightforward if you keep track. But this is the idea. Where do you talk? You do this all over in Math 53, right? Or somewhere? Maybe not that much. But you should. That's what we do. So what do I ask you to do here? I simply ask you to do this. I give you a bunch of black dots, and you should connect it by a parameterized spline like that. That's it. Then I go on and combine stuff from before and say, hey, I want to solve for something. I want to figure out where this design of mine crosses some line. How would you do that? It's this line crossing someone. That sounds like an equation I want to solve, right? So you go back to chapter 2. And in fact, I do tell you, use Newton. And finally, I ask you to evaluate what else would an engineer wants to know? How much material? How should you design this shape? Should you start from maybe I'm not a designer, but maybe he has a big metal rod that is heating up and bending, right? He wants to know how long it should be. So how do you what's the length of this curve? Is that obvious? In calculus, they told you how to evaluate parametrized curve, and you might remember this stuff. And in fact, I taught Math 1b many times, and coming up with functions that are interesting and non-trivial, but we are able to do is really difficult. It's just not easy to integrate functions, right? So that gives the setting perfectly well for chapter 4 here. You need to do this numerically. So what I said in my announcement yesterday is that you can do this in a week. We will start talking very soon about how to integrate functions numerically. But that's the problem. Like the previous one, this is not a lot of code when you get it right. It's quite straightforward. So as always, start early with it. Anyway, good. Let's jump on to chapter 4. Numerical differentiation and integration. Differentiation is kind of a smaller part, but it comes later. Integration is huge. How to integrate things numerically. Very important. The idea here is the following. Let's start with derivatives because that's easy. You just want to compute the derivative numerically. Why would you want to do that? Pretty obvious answer, I think. Why? So you give me a function f. I think in most of your homework problems, they are too superficial because they're actually functions. But in the real world, maybe they're not. So you don't know the derivative. And then you want to run Newton, and Newton needs the derivative. Or you need the derivative for any other reason. Derivatives are important. They are telling you the rate of change of the function. How do you estimate it? And I think most of you would figure out the more or less naive solution of forward, backward differences. Okay, a difference is a minus b, right? So it turns a derivative into a difference. And it's pretty obvious because it's right according to the definition of a derivative. You have a function f of x, and you're standing at a point x0, and you want to evaluate the slope here. This is the slope f prime evaluated at x0, right? But you don't know how to do it. You don't have that expression. You have no way to do it. One way to do it is to, of course, evaluate this value, f of x0. And then you jump a little bit to the side. This is why I mentioned that this is related to my little trick of understanding divided differences for Hermite. We jump a little bit to the side. Let's call it h. And we evaluate again. Okay? So those values are f of x0 and f of x0 plus h. And then we just do the straight line between those, and we pretend that's the derivative. So we do this straight line. Right? It's getting a little messy, but it's pretty clear. So the slope of this line is f of x0 plus h minus f of x0 divided by the jump, h. Trivially from a line, right? So now you would argue that if the function isn't too crazy, this should be an approximation to that. But there's not a lot of science behind it. So let's put some science behind it, put some numbers, error estimations, etc. But this is the idea. And also let's improve it because it's really bad. There are better things you can do. You probably saw already in math, in the calculus, that it's better to do center difference. It's actually better to jump over here as well. Well, I'm going ahead of myself. Clearly, it's completely symmetric to put I could put a point there and go backwards instead. You see why this one was called a forward difference? Because I'm standing at x0, and I'm taking a step forward and approximating that, right? I could do the same thing backwards. A much better thing is to do backwards and forwards and do what's called a center difference. And we'll find that formula soon, and we'll see that it's quantifiably much better. We can put numbers on exactly how much better it is. Yeah, so what is this? Another way to motivate this, we'll motivate it with Taylor, but this is the definition of the derivative at point x0. It's just that I didn't take the limit. So you kind of, so if you think about delta epsilon proofs, it really means that this should be fine if you make h small enough, right? Because it is the definition of the derivative in the limit, which means that for any accuracy level you want, is that what you call epsilon or delta? I always mix them up. You can find the other ones such that you're close enough, right? So this is the whole idea. All right, how do we do this? Well, we already did it. We have the expression. But how do we analyze this? Calculus doesn't usually tell us those error estimates. Calculus says in the limit it's fine and we don't care what's happening on the way there. In numerical analysis, why don't I set h to 0 in my computer? It's kind of stupid, right? Then it's obviously f of x0 minus f of x0. That's going to be 0, dividing by 0. So that's the point about the limit, that it's a limiting process, but you can't really go exactly to the limit, right? Why don't I set h to 10 to the minus number of atoms in the universe? I mean, what's the limit of how small I can make it? Eps, yeah. So the computer is not perfect, right? I mean, and this would be great, math-wise, to set it to as small number as you can ever imagine. It would be great. But then you will hit those issues we have the computer, that you can't really go beyond the 16 digits. You will start losing accuracy. So there's a threshold of how good you want to do this. And so we need to understand it a little bit better. Anyway, so here's one way to do it, just to connect to the previous chapter. What is this straight line? It's a Lagrange polynomial of degree 1 through 2 points. Well, kind of trivial, right? But the good news is that we had an epsilon we had an expression for the error for a Lagrange polynomial. So if I want to put, I remember I said already back then, why do I like the Lagrange polynomial? Because it's an explicit expression. I think I mentioned already before, we can, for example, differentiate it. So to derive a more formal expression that will, of course, return this, but also plus an error, which is more or less formal, why don't we just take the Lagrange through that and that point and differentiate it? That's the plan. So, that's what I'm going to do. And we'll see what comes out. And you'll see some interesting points about it. But Lagrange polynomial for f, the function f, with the points x0 as itself, but x1 is going to be this point that jumps to the right. So it's as trivial as I said. It's really a straight line through those 2 points. OK, let's do it. Do you need maybe actually, this is a great opportunity to put up the Lagrange expression. Remember? And the reason I like it is this slide, that we have the error term. But you remember these L's. You just got to keep track of it. Now you really see, I'm going to write down the polynomial. If I had to solve a linear system, that would be bad. So this is one of the powers here. And we're going to generalize and do, when we, for example, analyze these midpoints and other, we need more than this. Or midpoint word. But when we do second derivatives, we need higher degree polynomials. So we like the idea that it's a Lagrange, and we can just write the first point value times what we call L0, right? That magical polynomial of the right degree that is equal to 1 at one point and 0 at the other ones. And you could just follow the formula, but what it ends up being is going to be you do x minus all the other points. I'm standing at x0, so I got to do x minus all the other points, which is x1, which was x0 minus h. And I'm done because it's really just a straight line. Then I divide by my evaluation point, Then I divide by the same thing, but plugging in x1 there. Sorry, x0 there. So that's x0 minus x0 minus h. All right? What I did was I identified that this expression here, well, it's basically this last one here. When you're doing the 0th one, L0, it's going to be in the numerator x minus all the other points. And in the denominator, same thing, but replacing x by the 0, x0. Okay? So I know it's easy to make mistakes here, but that's really how simple it was. The other one says that now I'm standing at x1, so I better do x minus the other points, which is now x0, divided by same thing, but inserting x1, which is x0 plus h. All right? And you see that I'm not calling this p. So notation-wise, I cannot say that I'm done. I need to add. What am I going to add? The error. You see, if I want to call it pf, I better make it polynomial plus error, right? So here we're going to have now, what does this do? So there's the same product, but now we include all of the x's, right? You see, it's x minus x0 and x minus x1. So let's start with that. X minus x0, x minus x1, which is x0 plus h. Then I seem to be dividing by the next factorial here, which is 2. And then there is this annoying psi that we never get rid of, and it's, of course, a second derivative. So this is kind of what I'm after, this error term, to be able to say how good this is. And it's a function of psi here, which is a function of x. And that's kind of sad, but that's what it is. Yeah, that's kind of it. Oh, I should never erase that. I wanted that, but you'll be fine. I want to do one step of simplification just to see how easy it is. You see we cancel out some stuff here, and it ends up being fairly easy. It's really just f of x0. Well, I won't cancel out too much right now, but it's x minus x0 minus h over minus h. This one here is really just f of x1 times x minus x0 over just plus h. And the error term, I can't do much with right now. It's going to be x minus x0 minus h half f two derivatives. So the only thing I did was to simplify these denominators. But they're really just dividing by h. What was my next plan here? This is that straight line. I wanted the slope of that straight line, right, which is the derivative. So let's differentiate the straight line. We can do that. Sorry. This expression is, of course, the entire function. So the first two terms here, that's the straight line. I'm going to differentiate the entire expression to get an expression for the derivative. So differentiate to get f prime at x equals, well, the good news here is that this is really just a linear in x. See that? It's kind of straightforward, actually. It's going to be f of x0 divided by minus h. This here is also linear in x. That's going to be f of x1 divided by plus h, right? Sounds like this entire thing is, and sorry I'm mixing x1 and x0 plus h, but sometimes it doesn't matter. So let me go back to 0 plus h. Is this the only place I put x1? If you don't mind, x0 plus h over h. All right, are you happy? That's kind of shows that we did something right so far, because that's exactly the expression we wanted. And the only reason I go through all this is that I want the next term. And you'll see that that's not so easy, because of this annoying psi that always causes us trouble. First of all, this is not a linear in x any longer. It's a quadratic. We know how to differentiate that. This, there is no way we can differentiate, but there is a nice trick. Something nice will happen. But it's still a little disturbing. So first of all, it's a product of two things, right? So let's do the product rule. And we start by differentiating this guy, and it pops out 2 of these x minus x0s and the minus h. And we still have to divide it by 2. So that's the derivative of this function which you can see by saying it's x minus x0 squared. So the derivative of that is 2 times x minus x0. But then there is an x minus x0 times minus h. The derivative of that is minus h. I really just differentiated a quadratic polynomial. And then you keep the f prime xi. So the problem here is that the xi depend on the x. You don't know what xi is, right? Which means that it depends on x. So now we need to do another term where we keep the first term as it is, x minus x0 minus h, 2. And then we differentiate this other guy. And I have no idea how to do that, so I'm going to say differentiate with respect to x. I don't know if you've seen that notation, but you'll understand it. The derivative with respect to x of this function. Okay, and you all see why I didn't call it just, you see why I didn't put an extra prime there, right? Because it's the chain rule here that there's a xi going in there. That would differentiate with respect to the wrong thing. And this just demonstrates that it's impossible. I can't do that. OK, so what's the bad news I've covered? What's the good news? A little subtle, actually, but you'll see it. This is an expression for f prime of x. What do I want? I'm trying to estimate. We did it before, actually. I said this was a good approximation of derivative. Which derivative? Yeah, so I call it forward. And by that, I meant that I'm standing at x0 and looking forward, right? So really, what I said before was that I wanted this to approximate f prime of x0. OK? And actually, it's not only. It could be an approximate to f of x1 as well, right? But we'll do that later. But what I did was that this is an approximation to the derivative of f of x0. Why is that a good idea? Most importantly, this term, when you plug in x equals x0, the whole ugly thing that you don't know what it is dies. So that's really good. This doesn't completely die, but almost. So that's the reason it works out. You plug in x equals x0. And you get almost the final expression here that says that f prime at x0 equals f of what we want, namely this forward derivative. And here comes the error term. So as I said, plugging in x0 kills that, and that entire thing is usually just this minus h half left. And there will, of course, be a term depending on the second derivative and the xi, right? But that's OK. A lot of work just to get this guy out. But that was mostly just doing all this algebra and some calculus, right? I mean, in principle, it's kind of straightforward. That's the power of having these expressions for Lagrange, that we can do these things. More importantly, imagine, at least in principle and with a computer, you can do a lot of stuff now. You can put more than 2 points. You can do a lot of stuff and just do the same procedure and get these guys out. And just for completeness, the xi is not just anything, right? It's, does it say in the slide? Yeah, it has to be between the points. And the points are, well, it's the entire range of our interpolant, which is x0 to x1, which means that it's fine. It's really just all the points between x0 and x1. I always like to do simple examples, and my simple examples are so simple that they might miss some points, but it's hopefully capture something relevant. So for derivatives, I love this function. I love to evaluate it at 0, because then the value is 1 and the derivative is 1. And let's just choose an h here. So what this says is that f prime at 0 is approximately, now I'm just going to write the forward difference, e to the 0.1 minus e to the 0, which is 1 over 0.1, right? That's what a forward difference is saying, telling us. And that's about 1.0052. And you know the reason these numbers are nice is that you know that the answer is supposed to be 1. So it's pretty good, I think. You could reduce h. But let's use the formula just to see how good that is. Estimate error. The reason I know that the error is 0.52 is that I know the true answer. In general, you wouldn't be doing this if you knew the true answer. So you want something like that to estimate the error. And how do we do that? Well, the last thing I often refer to as an error term, because this is really the error when you plug in, when you substitute f derivative by this here. So I can estimate the error by h half. And I like to take absolutes of both, right? So there's an h half. And then there's this second derivative of evaluated at xi, right? What's the second derivative of f? It's still just e to the x. What xi should I use? It has to be between 0 and 0.1. 0.1, right? This is the stuff you did so many times before. You got to maximize it. You got to do the worst case. So it's e to the 0.1. And that's apparently 0.0553. Pretty good estimate, I think. Isn't it? So it really told us pretty accurately, even with this pessimistic estimate, that what the error was. Let's see, of course, bringing down h, things would get much better. In fact, let's see if I have that in the slide or if I can tell you already now. What is the rate of convergence here? Why is my password incorrect? Did I just change it? Caps lock? No. I've typed this password a lot of times. I think my computer is somehow not. There we go. Weird. Anyway, yeah, what is the rate of, do you like this? I mean, looking at this, are you happy with this? So to you at this point, the way I describe it, there is no reason we can't set h to the 10 to the minus 8. And then this would be extremely accurate. So let me just give away a little bit about the future. A huge part of this course, I haven't talked about chapter 5, which comes after this. It's solving differential equations. Okay? That's really one of the big uses of numerical analysis. Solving differential equations. We're going to use these things in differential equations. The problem with h then is that the smaller h you have, the more work you have to do. So you can imagine that if you want to go from 0 to 1 in steps of h, it's really bad if h is 10 to the minus 8. So this will matter a lot. And for whatever reason, just accept that it's not, you don't want h to, it would be great if this was accurate without h being too small. Okay? And is it? Well, at least it's convergent, right? We said by the limit and everything, it's fine. It's going to converge. But it's really what we used to call in chapter 1 that the rate of convergence here is really just order h. So if I divide h by 2 here, if I do 0.05 instead, this will really be something like 0.26 or something, right? And it would. And that's just not good enough usually. But it's, we want better. So let's see what we can do better. Oh, it was the wrong password anyway. I think my computer is broken. Probably the keyboard. I'm going to reboot it. That's a desperate attempt. I need to restart. All right. Yes. Anyway, so how do we improve it? I kind of indicated already in my figure I erased that there are other things you can do. The first obvious thing is that you can go backwards instead. And this, if you like to do that, you can just set h equals to minus 8. Remember, I never said that h was positive, right? You thought h was positive, which it is, but I don't need that. So turn h into something negative, and you realize that we're going to the left. And we're dividing by negative, so usually you shuffle the terms. And you call it f of x0 minus f of x0 minus h divided by h. That's the backward difference, completely symmetric, and this term is the same, maybe with the sign being plus instead. Okay? But that's not fundamentally different. That's just another. That's just another. Oh, now I got my Unix. Sorry, I don't want Unix here. I should have started it into Windows. Don't worry, I know what I'm doing. I think. I better stand here now and catch it. All right, fine. So what we're going to do is to introduce more points. And the plan is that what we did also, I'm not going to derive it for all those points, but it really in principle works. There we go. Works as well for many points. So let's look at the 3-point formulas. What happens if we choose 3 points? Let's say you do 3 points of the following form. Let's call them x1 for now and x2. 1, 2, 3. What's the analog to what we just did? There are different ways to do it, but remember I took 2 points, I put a straight line between them, and that slope was my derivative, right? Sounds like I'm going to put a quadratic between these 3, differentiate and evaluate at x0, right? You see how this generalized to a whole class of methods, whatever you want. Or in words, take your points, fit a polynomial, differentiate the polynomial, because you know how to differentiate. This was my motivation for chapter 3, for fitting with polynomials, that polynomials are easy to differentiate. This is exciting. Is this going to work? It did. Huh. A little freaky. All right, at least now I get my slide. This summarizes what we did. Just result is that formula, right? That's the forward difference formula and the backward difference formula. Generalizing this entire procedure to 3 points or any number of points gives you this. Namely, you just plug in, this is nothing new, this is the Lagrange form exactly from before. Namely, in general, n plus 1 points, right, with all these L's, and this general form. And all you do is that you differentiate this entire expression. And what's going to happen is that, of course, just like before, you'll end up just differentiating each of these individual L's. That was trivial for our case, because it was a straight line. So that gave us this whole chunk here will give you the difference approximation. So if you don't care about if you want to gamble and just get the formula out, like in this case, if you just want this formula out, you're done. You just differentiate these L's and you're done, right? If you want some rigor to this and be able to have an error formula, you got to differentiate the error term as well. And you can actually see that it's possible to simplify it out kind of nice with the same assumption that when you plug in a point xj, remember what happened? I had to erase it, but when it was a general x, there was no way you could simplify in because of the derivative of this f. But exactly the same things happen in general case, that when you plug in one of these points, you will kill the bad term. So it's actually good news. You can plug in any of these j's here and get out the formula exactly. This fits exactly what we did before. But you get a product of terms, and you get the next derivative evaluated at xi you don't know. But that's how we like error formulas. So with this, you can just keep on cranking out formulas. Let me show. So here are a bunch of them summarized. But let me show how to derive the 3-point, because that's kind of good to know. So for the 3-point, yeah, it's really just algebra. I think it's better I go to the second derivatives. So let me skip the 3-point and tell you what to do instead. So you can imagine me choosing these 3 points and computing L's for them all. Remember what L's look like? They are, I'm going to come up with an L that is equal to 1 here, and etc. Right? I'm going to, they are the L's in that formula. I'm going to differentiate those L's. And if you thought it was messing with my x0 and x0 minus h, it's going to be all of these x0 and x1 and x2 all over the place. And you'll get the formula out. And that can be done. It's completely just routine. The error term, of course, will just be a bunch of products of those and an unknown term of the higher derivative of f. So this can be done. What you realize pretty quickly is, similarly to the divided differences, why don't we just simplify things a little bit and say that things are equidistant? OK? And then you can imagine that these expressions that will involve a lot of x1 minus x0 and stuff will simplify. OK? So that's usually what's done, but it's not needed. But if you make all those assumptions, you get the following formulas, commonly used formulas. So I'm having equally spaced points. I call it h, the distance between 2 neighboring points. And here are things. Let's go through everything. So if you want to go to 3 points, we did 2 points. If you want to go to 3 points, here's a funky formula. Maybe you want to focus on the second one first, because that one I think you've seen before. It's called a center derivative. It says that instead of doing one step forward minus yourself, you do one step forward minus, let's keep on going here, x0. Instead of going up here and doing that minus yourself that we did in the forward difference, why don't we go one step backwards and draw that line? And just visually, it seems like it's going to better approximate the actual slope there than the slope from before, right? And that's just an intuition. But it does actually use 3 points. It looks like a 2-point formula. That's because of the symmetry. It happens to just not want to use x0. But it's a 3-point formula. Maybe confusing, but we call it a 3-point formula. It's fundamentally better. It's the center difference. So it's dividing by, of course, 2h, because the distance here is now 2h. But you don't have to think too much. You could just plug in all these expressions. So this is a very widely used formula. What tells me in this line that it's much better than before? Kind of the most important thing to look at. After looking at the formula itself, you go to the error term, right? And there's, of course, an F3 of psi, which was expected and not too interesting. H square. This tells me that it's just fundamentally better than before. I killed my MATLAB, but let's bring it back to life. If I do that with the same numbers here, you will probably see a much better result. What else can you do with 3 points? Well, in principle, there are just 3 choices, because remember, I insisted that you estimate the derivative at one of these 3 points. If I don't know how to do the error term. So there are 3 choices. I just did the midpoint. I estimated the derivative at the midpoint using these 3 points. And the answer was that minus that over 2h. What if I'm standing here and want to estimate the derivative at this point using these 3 points? You could call it a forward difference, but using 3 points. I can, of course, also stand here and look left. That's not too interesting. All of this gives you formula number 1 and 3 here. You see, I'm standing at x0. I'm going one step to the right and one more step to the right. And I'm getting a quadratic h error instead of linear. So there are many ways that you can do better than the one to the right there, the forward difference, right? And that's one of them. Just showing how good the centered can be, e to the h minus e to the minus h divided by 2h is enormously much better than the forward difference with the same h. Yeah?
Does that force your h to be less than 1? So if you have like a problem where maybe steps with 1 is still too small, then it doesn't really help?
It's a good question. We had these questions when we talked about rate convergence and everything. Why is h squared better than h? We always say that. H squared is better than h, right? But you're right. If h is 2, then h squared is bigger than if h is 1, right? So the answer is that, all these h's are expected to be small in some sense. There's a big constant in front of it. And it doesn't kick in. But the answer is really that, no, if h is too large relative to what it should be, the error will be worse. It's kind of saying that if you have these 3 points, and if the function is completely crazy, I don't know what a good function would be, but if it's not smooth and nice, but looking like this, you're actually making a smaller error with that than with that. In my example, it doesn't, but that's what it's saying. H has to be small. So we call it h squared. You should see it as a limit as h goes to 0. Eventually, at some point, it will be much better than the linear one. Because you're right, for h squared, of course, sounds like an increasing function for large h. Anyway, super small error. Well, we can try it with this. But there is a constant, so it's unclear, right? But in principle, what we're talking about is what if you do what if you set h equals to 1? Then this is the center difference. It's not too bad, actually. While this is the forward difference. And it's much bigger. But there is a constant in front of all these that matters. So let's bring it up to h equals 10. That's pretty bad. So now we're in a regime where h is so big, so it's just not. It's telling me that the derivative, did I do something wrong? No. It's just so horrible. The e function blows up, right? And I'm drawing a straight line to estimate the derivative. It's just very bad. And it's less bad to do this. About the same. Anyway, at some point, I'm sure that one exploding with h squared would be worse. So h is small. Otherwise, it's not going to be accurate. And by the way, the error formula will tell you how bad these h's would be, because this would be e to the 10, which is a huge number. So that's the reason we want to put some science on what we set this number to. I have one more formula. Look, so these are basically the formula, 3 of these. We've done most we can with 3 points, equidistant, right? We evaluate all the 3 points. It gives some nice formula, and we're going to use them a lot later. Before we do the second derivative, look at the bottom here. Why not 5 points? The more points, the better you should be able to do. And indeed, you can bring up the error now to an h to the 4 if you use this last formula. How do you derive this last formula? Exactly like I said. It's just a mess. But a computer can do it. You just plug in into the expression on the previous slide, and you get everything out, including the error term. So it's a nice framework. And the big setting here is not really what I said, namely that you want to evaluate the derivative. It's solving differential equations. So this will come back a lot in chapter 5. And you will also see why we need all of these 3 here. You might ask yourself, why on earth would you want this one-sided formula when you can always use the centered? Well, here's an example. Suppose you have a function that starts here and goes like that, and you want to estimate the derivative there. Can you use the centered? Well, suppose that this function doesn't exist here. It's not defined. If you run it in MATLAB, it will say, I don't like negative numbers. OK? You better then do what's one. And this is exactly what's going to happen for the differential equation. At these boundary points, you better then use a 3-pointed formula looking forward like that instead. So that's the setting. Anyway, let me tell you a little bit about the second derivative. You see the fourth equation here? That's a second derivative formula. How do you think we do that? In principle, you could do the same thing. But since it looked a little messy with that error term as it was, it's going to be even worse now. So here's an easier way to do it, an alternative way to do it. Second derivatives. You start with a Taylor. You take Taylor of the function f about some point x0, and you evaluate it at, and this I'm going to tell you immediately that it's a 3-point formula. So I'm doing this here. I want to estimate the second derivative here using these 3 points. How do I do it? This looks messy, but it's going to simplify nicely. So you have f of x0 plus h. What does Taylor tell you? It's a constant f of x0 plus the derivative times the delta x, right? And I'm going to keep on going. You get a half of the second derivative, h squared. I need 2 more terms. I'm going to run over onto this one. It's going to be plus a 1/6 of the third derivative of x0 times h3. And then let's terminate by a 24th of the fourth derivative. And then we evaluate that at some point xi times h4. And I'm going to call it xi1. All right? Looks messy, but it's just Taylor. F at x0 plus h is f of x0 plus the derivative times h plus the derivative times h squared half plus the second derivative plus the third derivative times h cubed 6. And then I terminate, and then I better put xi there. OK? Now we go to the left and do the same thing. F of x0 minus h. What's going to be different? And this is the key to why this will work out a nice formula. A lot of symmetries here, right? Well, you could just write it first if you want to. That's the same. The h now became a minus h, right? So I'm getting a minus sign here. What about this one? Minus h squared. That's h squared. So this is identical. What about this one? It's a cube. So I'm getting a minus sign. And this one, I don't care if it's it is a plus, but the problem is that it's not the same xi, right? Remember, we don't know anything about xi. So when you terminate, it is what it is. So let's just look at the first part. Do you see how this can tell me a nice expression for the derivative, including an error term, in one simple step? This is what you want to approximate, right? What if you add these equations? All you know is f. You know values at the points. But you don't know the derivative. You could estimate that first and then plug in. But let's say we don't want to do that. You want to eliminate this term. And you do it by adding the equations. So adding those two equations gives you the following. Add, you get f of x0 plus h plus f of x0 minus h equals, we kill, well, we get 2. That shows up twice, right? How about the f prime? They cancel out. Then you go to the next one. That's the half. Adding these two, they are identical. It's really just going to be f2 primes times h squared. And now if this is all, if you approximate that this is the case, do you see now how we can approximate the second derivative? It's the famous 1 minus 2, 1 formula. 1 minus 2, 1 divided by h squared. So reshuffling here, you can solve for f double prime, right? But let's keep on going so we get an error term. What happens to the cubic term? It also disappears, which is nice. Let's see if we can do the error term. That's a little messier. Because the xi's are different, you get xi1 plus a fourth derivative evaluated at xi2, right? And the trick here is to actually say that this expression here can be replaced using the, let's just do this part here. Using the intermediate value theorem, you can write this as f4 evaluated at some other xi times 2. I just want to simplify it. I mean, at some point you can just plug in xi's. But if you're going to plug in one xi that I don't know and add it to another xi I don't know, I can just as well use the intermediate value theorem to tell you then there's another xi that I don't know that will be the sum of those two, right? So times 2. It's an ugly trick. But the end result ends up being that your second derivative at x0 is equal to, as I said, the famous 1 by 1. I mean, I multiply that by 1, and then minus 2 plus 1 times the last point. This is the formula, divided by h squared. And the error term can be written simply as h squared, I killed a 2 here, so it's a 12th, times the fourth derivative evaluated at some new xi that I don't know. And that's the entire formula. So I should have done this with Taylor as well, or with Lagrange as well, and you would have freaked out about all the derivations. This is a nice trick that worked out because it was symmetric. So I cancel things out. You have the entire formula here. What's good about this formula? What's good is that we got a much higher order than we deserved. You should not have expected this. Because why? Because this one was killed. That's the reason we got an h squared here. Okay? There's an h4 coming here, and I'm dividing by h2. So at the end, I have an h squared, which is great, but I didn't quite deserve it. Because the first term I killed off, I should have got this one to be the leading factor. What if it was not equidistant? What if this guy, what if you move this guy up here? You see a bad thing? Then these terms would not be equal with opposite signs, and the magic would not happen, and the formula would just be first order accurate. That's why we often like these. Symmetry gives you extra benefits. But the end result is a very nice and widely used formula that we will come back to a lot. In terms of this, it means that e of h minus 2 of e0 plus e of minus h divided by h squared should be an approximation to the second derivative of e to the x at 0, which luckily is still just 1, right? And you see that it's really accurate. It's a second order accurate formula. Actually, the number here doesn't matter. What matters is if I divide h by 2, this will be the fourth, the error as before. Is this new? I'm sure you've seen that formula, but without an error term. I think maybe not. But the forward difference, at least, we teach in calculus to some extent, I think. Just one final, I'm going to skip the Richardson, but here's a slide that I kind of like, so I'll tell you about this. I told you before, why don't you just set h to whatever you want? And here's the reason. That if you do that, you get round-off errors. And that can be analyzed. And it's quite nice, actually. So let me just run a little demo that I call diff demo. OK, you don't need to worry about the details here. Just the point it's trying to make. I make a bunch of steps, h. OK? So what I'm doing is I'm doing my experiment that was here before on a bunch of h's. And here they are. OK? I have 150 values of h ranging from 10 to the minus 15 to 1. OK? And I'm going to see what happens. And what am I doing here? I pick each of these h's. I do the experiment that we did before. In fact, here I'm doing the center difference. Do you see that? It's e to the h minus e to the minus h divided by 2h. So it's the middle experiment I made. Central difference formula on this. And then the true value is 1, and I compute an error, being what I computed minus what it should be, and I put it in a big list. All right? Outcomes, of course, for each of these h's, an error, and I plot it in a grid. What do you think this is going to look like? Here's the result. On the x-axis, you have the step size h that I used. It ranges from 10 to the minus 15 to 1. Okay? 1 we already saw was bad, kind of order 1 error. And then we did 0.1. So we were all the way very far to the right in my experiments. Now you keep on reducing, and it gets better and better. What do you think the slope is of that line? If I go 5 magnitudes to the left, how many magnitudes do I go down? It should be about 10. It should be a slope of 2, and that's because it's a second-order accurate method. Okay, so that's good. If I did it with forward difference, it will look the same. It's just that it will only reach about to halfway down. It would not be so accurate. Then what happens? What is this? It's random. It's weird. It doesn't look like our smooth, nice Taylors and things converging, right? And why does it look random? Who's responsible for this? Clearly, it's not true, right? Because my math told me that the error should keep on decreasing according to h squared. I'm doing the middle formula here. My math is telling me that this is the error. So if I keep on going left, it should just keep on getting better. So it's the thing we discussed before. This is the computer giving you the wrong answer. Rounding error. Okay? And it apparently kicks in at a point where things start getting worse. And then it's kind of random, because rounding error you can't control. To the limit that when it's 10 to the minus 15 or 16, you get complete garbage out. And you know why that is. Because if I do exp of 10 to the minus 17 as an extreme case, the computer can't really handle it. And it completely breaks. So at that level, it should break. But isn't that interesting? What's more interesting is that you can actually predict where it breaks. By just setting these two errors equal, you can get a nice expression for the h that is optimal. And this is practical because it tells you what h to use, if you can set it to whatever you want. This is the optimal h to use. And this is well predicted by that little demo. Anyway, that's a kind of a nice rounding up of these derivatives. I'll have office hours now. Come join me and ask questions about the programming assignments.